Good morning. We're going to do a little deriving today. And deriving is a process in which we take some equations we already know and we create new equations that will be more useful to us than the previous equations. So we'll start out using some equations we already know. So far we know that the average velocity is equal to the displacement over time. We also know that the acceleration is the change in velocity with time. And then we had this other equation, didn't use too much. It's just another way of finding the average velocity, which is the initial velocity plus the final velocity divided by 2. So using these three equations, we can derive 3 new equations, which might be more useful to us and will definitely be more useful to us. So the first equation comes from the definition of acceleration. So if we rewrite this as v final minus v initial over time, we can rearrange this to have an expression which will give us the final velocity at any point in time if we know the acceleration. So I'll multiply both sides by t, and then I'll add vi to both sides. So I get vf equals ta plus vi. And if you just kind of rearrange that a little bit, you end up with our first equation, vf equals vi plus at. I'm going to go on and derive the next one, so feel free to pause here. Our second equation of the big three is one that is intimately tied to this idea of acceleration. And all of these are scenarios, all these equations you would use in scenarios that involve acceleration. So if we look at these motion graphs, which we've been looking at for a few days, and we think about a velocity versus time motion graph. If our object is accelerating, it might start at some initial velocity. That could be 0, it could not be 0. And then it's going to constantly accelerate for some period of time, delta t, until it reaches a final velocity, vf, at a time t. Let's just say this is a general time. So we're interested in the displacement of this object. And we can find displacement using the area under the curve. We can also think about the average velocity, but in this case, the average velocity might be a little more difficult to find, but actually you can derive it in that way too. So if we think about the area under the curve, we have length times width here, and then we have that length times width divided by 2 here. So we'll just add those up. So we get d equals area of this square plus area of the triangle. So the area of the square is vi times t, and the area of the triangle is 1/2, we'll just pull that divided by 2 out in front, times vf minus vi over, oops, I messed up. So it's actually vf minus vi times t. So if we look closely at this, this is ultimately delta v. And from our acceleration equation, we can say that delta v is equal to the acceleration times the time. So we're just going to replace vf minus vi with acceleration times time times t. 1/2 was separate. So then if we combine these terms, we get d equals vit plus 1/2 at squared, which is our second equation. Kind of cool. We took something we knew and we derived a new equation out of it. So now we'll derive the last of these big three equations, and that comes from these two average velocity equations. So we're going to kind of combine these two equations. So we know that d equals the average velocity times time. We have another equation for average velocity that we've looked at, which is Vf plus Vi over 2. And if we look back at the acceleration equation, so if there's a Vi and a Vf, that means there is some change in speed, at least, or change in velocity. So we're going to look at both of these acceleration equations. So if I want to solve A equals delta V over t for time, I end up with time equals delta V over A, which is Vf minus Vi over A. So if I plug those two expressions in, Vf plus Vi over 2 times Vf minus Vi over A, I get to do a great thing that you guys probably are learning about in math, which is like distribute. It's kind of like foiling, but not really. So we'll take Vf times Vf gives us Vf squared. Vi times Vf gives us Vi times Vf minus Vi squared. And then we need to distribute that, so we say plus. So sorry, we did Vf times Vf, we did Vi times Vf. Then we're going to do Vf times Vi, so we're going to get negative Vi times Vf. And then we'll get negative Vi squared. So I think I got them all in there. And then all over 2a. So then we get d equals Vf squared minus Vi squared all over 2a. And if you keep going, you multiply both sides by 2a, so you get 2ad equals Vf squared minus Vi squared. You can end up solving for Vf by adding Vi squared to both sides. So Vf squared equals Vi squared plus 2ad. Woohoo! We ended up deriving all three of these big three equations. In the next video I'll show you some examples of how to use them.